Okay, let's take a look at 3.2, a proof of the Pythagorean theorem. And there are two things. Number one, what is a theorem? A theorem you've learned about already. A theorem is a statement that's been proven true. All right, and the Pythagorean theorem has been proven true multiple times. One proof that we're going to look at today, but there are many proofs of the Pythagorean theorem. And the Pythagorean theorem is a statement that states a relationship among the lengths of the sides of a right triangle and its hypotenuse. So the Pythagorean theorem has to do with a right triangle, where here you have a leg, and then you have your hypotenuse. Okay, so we already labeled these, but label these again. Those are your legs, and the hypotenuse, that is your C. So the Pythagorean theorem defines a relationship between the legs and the hypotenuse. Make sure that's in your notes. So Pythagoras is a pretty interesting person, whereas his followers were extremely devoted to him, meaning Pythagoras probably didn't even come up with this theorem. His followers just said, hey, he's amazing, everything we do is his, even after he passed away. So anyway, this is Pythagorean theorem, but it doesn't necessarily mean that Pythagoras was the one that thought of it or discovered it. And believe it or not, there was a time, so right here, their influence became so strong that some people feared that they threatened the local political structure. There was a time when politics was full of intelligent people. Well, I know it seems impossible in today's day and age, but there was a time when people went into politics and were actually intelligent and problem solvers. It's amazing to think how far we've come from that. All right, so if you look at your lab sheets, you have multiple different puzzles that look like this. Go ahead and find those and cut one of them out. It doesn't matter which one. I think I'm going to be doing the first one, kind of showing you how the first one looks, but there's A through D, so there's multiple puzzles you can choose. And what we're going to be doing is we're going to be arranging these and putting them all into these. Now, you're not putting them all into one or the other, or not all into one of them, but you're choosing which ones to put into square number 1 and square number 2. But all of these shapes, 2, 4, 6, 8, 9, all 11 shapes are going to fit into these two. Again, not all 11 will fit into 1, but all 11 will fit into 2. And we're trying to figure out which ones will fit into which to which squares and how they fit in there. And once we do that, we're going to be answering some of these questions. Okay, so once you get them in there, cut them out. I'll show you what they look like. All right, so this is the one that I'm going to be using. I'm going to be cutting these out and kind of showing you different ways to fit them in. So we're trying to get all of these fit in there. Cut them out. Try to fit all 11 pieces into those two squares, and then come back to the video to see how you did. Okay, so here we have all of our pieces cut out, and we're trying to fit them all into those two squares. Okay, so see what you can do, try it, and then come back to the video. Okay, so here we have the solution with all of those pieces put in there. And then go ahead and let's take a look at this and kind of look at some of the properties that we're seeing here. Why does this work? And if you do some of the other puzzle sets, the same pattern or similar pattern setup is going to be the solutions for those other ones as well. So now let's take a look at answering some of those questions within the text. Okay, so for part A, study a triangle piece into 3 square pieces. How do the side lengths of the squares compare to the side lengths of the triangle? If you haven't answered that question, go ahead and ask it. So you notice, or go ahead and answer it, but before you do, to kind of clarify, you notice there are 2, 4, 6, 8 triangles, and there are 3 squares. So you're comparing the lengths of the sides of the triangle to the lengths of the sides of the squares. Go ahead and answer part A. Okay, so if we look at one of these triangles, let's look at the shortest side, right here. You notice the shortest side is the length of the sides of the shortest square. And then if you look at the second shortest side, which is the other leg, right here, that is the length of the side, all sides of that second square. And then if you look at the hypotenuse, which is the longest side, right there, that is the length of your longest square side lengths. Okay, so those match up. And if you remember, well, let's go back and answer part 2. So we've answered part 1, the relationships of the sides of the triangle to the relationships of the sides of the square. Each square is equal to the length of one of the sides of the triangle. And then part B is what we just did. We did that a little bit earlier, but arranged all 11 puzzle pieces to fit exactly into the 2 puzzle frames. We've already done that. What conclusion can you draw about the relationship among the areas of the 3 colored squares? What does the conclusion you reached in part 2 mean in terms of the side lengths of the triangles? And compare your results with those of another group. Did that group come to the same conclusion? Okay, go ahead and try to answer part B looking at your solution that we had filled in. Look at part B and try to answer 1 through 4. So if we look at our solutions, go ahead and draw these on your page if you need to draw them on the page, but I just kind of color coordinated everything and how things fit together because we're going to talk about why they fit together this way. Easiest one is if we look at the right, a solution on the right. Now, what I did is I took the biggest square, okay? But before I did that, I set up the smaller triangles in a way so that they would all be the biggest side, the longest side would be facing inward. And when I did that, it created a perfect square where all of the sides were the same length as the hypotenuse, right there, the longest side. Okay, and then over here, what I did is I knew that the smallest square had to line up with the smallest sides. So when I put that in the corner and I put the smallest side against that, I saw that I was able to fit 2 triangles in there to make a sort of a rectangle. But then I also noticed that when I did that, that the side that was facing out, those were equal, and those were equal to the side length of the medium square, and so that's why the medium square fit perfectly in there. So take this moment and go ahead and answer all of part B, 1 through 4 in your notes. Okay, we did 1, 2. What conclusion can you draw about the relationship among the areas of the 3 colored squares? So those 3 squares, each one of those squares is equal to the side length of one of the triangle. All the triangles are the same, so there's not different triangles. But if you set them up, it would look something like this. Let's say this is one of our triangles. If we set up those squares, one of them would fit perfectly over here. Another one would fit perfectly right here, that medium one. And then the longest one would actually fit perfectly over the hypotenuse, like that. Okay, so they equal the length of the side lengths for the triangle. And then also, when you think about how we set this up, in the box on the left, we put this square, and 4 of these, right? 2 for this one, 2 for this one. Those were all in the box on the left. Let's take a look at that. Okay, so yeah, we have the little one, the little square, the medium square, and the triangles that are associated with them. 2 triangles per each one, right? So this squared, and then 1, 2, 3, 4 triangles. Box on the right, then, we have the big square and 4 triangles. So what this means is, since they were able to fit in there, this squared right here, this square, plus this square is equal to this square. All right, so that is the proof for the Pythagorean theorem. These two squares right here equal the larger square, the area of the larger square. So what we were able to do is we were able to put this square right here and this square right here in a space where it equaled the same area as this. I know it doesn't look like it, but it is. It has the same area. Okay, so that's the Pythagorean theorem. That's kind of what you're talking about on part 2. Part 3, what does conclusion in part 2 mean in terms of the side lengths of triangles? Well, there's a relationship between the side lengths of the triangles. Okay, and that relationship between the side lengths of the triangles and what they're talking about with the side lengths of the triangles is, let's remember we had that as A, B, and C. Well, I know that when I take a squared, because this is right here, this is a squared, and this is b squared, I know that those two added together are equal to c squared. And then number 4, compare your results with those of another group. Did the other group come to the same conclusion? So then you're talking with other groups if you're working in class for this one. Otherwise, let's jump on to C. Suppose a right triangle has lengths of 3 centimeters and 5 centimeters. Okay, so let's go ahead and draw that out. That's what our triangle is going to look like, and it's a right triangle. Use your conclusion from part B to find the area of a square drawn on the hypotenuse of the triangle. Okay, so the first thing I'm going to do is we can draw the squares off of this. So let's go ahead and do that. So here we drew the squares off of, here's our original triangle. We drew the squares off of that thing. Now remember, when we're looking at this, we know that the area for this one is 3 squared. The area for this one is 5 squared, because the area of a squared is the side length, which is this, squared, up to the third. And the area for this is, we don't know what C is, but it's the side length, it's the hypotenuse, right? So then if we set that up, I know that the sum of those two squares, which is 5 squared and 3 squared, have to give me C squared. All right, so let's go ahead and simplify it from here. So if you haven't done this, see if you can't figure out C from here. Pause the video and see if you can't figure out C from here. Because when we simplify this, this is 25 plus 9 equals C squared. 25 plus 9, that gives us not 35 but 34. Okay, so C squared, this right here, that is equal to 34. Whoops, not 3 to the 4th, 34. Now remember, our goal is to figure out what is C. Well, if C squared is 34, then C, remember, so 34, that's the area. This represents the area of the square. Okay? Because C squared, that's the area of the square. And so remember, we've already learned that, hey, if we know the area of the square, we can easily find the side length by taking the square root of the area. So C has to be square root of 34. That's the exact length of that hypotenuse. All right, so we found the length of the hypotenuse, and then in D, in problem 3.1 and 3.2, explored the Pythagorean theorem relationship between side lengths. State this rule. So see if you can't come down here and state what you think the Pythagorean theorem is We've already done this a couple times, but see if you can't just write it out. So here's the Pythagorean theorem. It works, remember, only for right triangles. So we have a right triangle. We're going to label the legs A and B and the hypotenuse C. So the Pythagorean theorem is simply when you square A, add it to B squared, that gives you C squared. And again, these are the areas off the squares off of those sides. Okay, so this right here is the Pythagorean theorem. Make sure you have that in your notes, labeled similar to this. And that is it for 3.2, a proof of the Pythagorean theorem.